In this video, there's another example of a recursive model for counting and also another example of a combinatorial proof. In this example, we're counting the number of ternary sequences. So ternary sequences, remember, means that we're allowed to use the symbols 0, 1, and 2 in our, in our sequence. We want the sequence to be length n, and we want there to be no consecutive 2's. So the first few values, so the subscript here, when we say t sub n, the n that we're referring to is the length of the sequence. So t sub 1 is referring to sequences of length 1, and not only are there not very many of them, but it's impossible for any of them to violate the condition, because the condition says you can't have two 2's in a row, and these things don't have 2 of anything in a row. So that'll be all of the possibilities of length 1. T2, on the other hand, is 8, because there are 9 possible sequences altogether. You could have 0, 0, 0, 1, 0, 2, 1, 1, I'm sorry, 1, 0, 1, 1, and 1, 2. And you could have 2, 1, and 2, 0. So it's a long way to go, considering the only sequence you can't have is, 2, 0, 2, 1. The only sequence you can't have of length 2 is just the 2 2's in a row. So it's all but that. So that's T2 will be 8. Let's give a little bit of thought to T3. It's going to be a little big, so I'm not going to list the whole thing, but I can at least think about how I would organize this. If I'm counting T3, then I'm filling in 3 blanks. And so those 3 blanks that I'm going to fill in are either going to start with a 0, or the 3 blanks are going to start with a 1. And what I'm looking at here is the ones that start with 0, I'm kind of keying off of this. And the ones that start with 1, I'm kind of looking at this, just to see what happened before. And the ones that start with a 2 are the only ones where I really had to do any thinking about it. So when I start with a 0, the next 2 digits can be any of these guys, and it'll be fine. In fact, it can be any of all of these guys. Any of these things I built for T2 can be in the 2 blanks here, because you can't possibly introduce consecutive 2's into that problem. So that means that there's going to be 8 of these, namely a 0 followed by all of the ones I listed when I listed T2. The same 8 things can happen in the blue ones. So I can have a 1 followed by any one of those 8 things that are above. And so that's 8 more, so there's 16 altogether at that point. And then when I have the 2's, then I have to actually think about it. When I start with a 2, and I want to finish the last 2 blanks, then the second digit has to be either a 0 or a 1. So any sequence that starts with a 2 either starts with a 2, 0 or starts with a 2, 1. And so I'm sort of thinking of these 2 cases as sort of corresponding to this case up here. So the question is, what can go in the blank at that point? Well, at that point, I'm only filling in 1 character, and there's nothing I can possibly put there that's going to cause a problem with consecutive 2's. And so any of the single characters from here can go in that final blank, and that'll be okay. So what that means is I'll have 2 of them that look like that. I'm sorry, 3 of them that look like that. I could put a 0, 1, or 2 in that last blank. And there'll be 3 of them that look like that. 0, 1, or 2 in the last blank. So altogether, T of 3 is 8 plus 8 plus 3 plus 3, which is 22. So there will be 22 of them, but I can think of them as being broken apart based on how they start. And so the reason for doing that is that that's really what happens in general. So if I think of that I'm solving the problem where I have length n, so in other words, I'm counting T sub n now, with the subscript as n. If this whole thing is length n, then the blank has to be filled. I'm just going to move this over. So if the whole thing is length n, then the blank has to be filled by a sequence of length n minus 1. And that sequence can't have any consecutive 2's in it, or else I would have consecutive 2's in the whole thing. So with no consecutive 2's. Well, that is exactly the description, the number of these. That's the exact description of t sub n minus 1. That's exactly what t sub n minus 1 would mean. T sub n is the number of ternary sequences of length n with no consecutive 2's, so t sub n minus 1 is the number of ternary sequences of length n minus 1 with no consecutive 2's. So there are t sub n minus 1 things I can fill in the blank. That'll be the same reason, I'm not going to try to write the words again, that there will be t sub n minus 1 possible ways to fill in that blank. Again, because the first digit is 1, so the rest of it has to be length n minus 1. In case 3, this is a blank of length n minus 2, and so there will be t sub n minus 2 of these. T sub n minus 2 ways to fill in that blank, and t sub n minus 2 ways to fill in the blank below. And so the 4 cases, if I add those together, and I'll go ahead and get rid of this slowly and in small pieces. Then what I've shown is that when I'm trying to count the ternary sequences of length n, that's t sub n, that breaks into 4 cases, one of which has t sub n minus 1 ways, another one has t sub n minus 1 ways, one has t sub n minus 2 ways, and the other one has t sub n minus 2 ways. So that is t sub n is twice t sub n minus 1 plus twice t sub n minus 2. And of course, we have the initial conditions that we found at the very beginning, namely that t1 is 3 and t2 is 8. So that information together determines this sequence. You'll see that that does correctly predict what t sub 3 is going to be. And then we could use that same recursive formula to find t sub 4, t sub 5, t sub 6, and so on without listing everything out. For the combinatorial identity, I just have another example problem here for you. This is a kind of a weird identity about how things multiply together. And I've kind of written it in a suggestive way. Notice I'm using the stacked notation here just because it shows up better than the C notation when you're trying to show multiplication. But another way of writing this is that when you multiply k times n choose k, you get the same thing as when you multiply n times n minus 1, k minus 1. n minus 1 choose k minus 1. So that's another way of saying the same thing, written more in the C notation. But these are the same. So our goal is to find a counting problem where we can answer the question 2 different ways, and therefore those 2 answers are the same. We can tell from the fact that these are products, these answers are products, that I'm going to answer those by doing a 2-step algorithm to count something. So the question I'm going to use here is the one that you see in front of you. If I have an organization with n people, so that's a club, I want to elect, well, I don't want to elect, I want to select a k-person committee, and I want to designate one person of that committee to be the chairperson. This is one of the counting questions that we answered in section 5.3. So I can do this in 2 different ways. One way would be to do a 2-step algorithm, where step 1 is choose the whole committee. So I'm going to choose k people for the committee. And this is what you might do in real life if you were organizing this this committee. You might elect the committee first, or select the committee first, and then let the committee decide on who its chair is. So the committee could elect their chairperson. But they're choosing the chairperson from the people that are on the committee. So if I think of it that way, there are n choose k ways to do step 1. And then once you have the k people that you've chosen, if you have to pick someone from the committee, there's only k ways to do that. So basically k choose one. Of the k people on the committee, you're going to choose one to be the chairperson. So the total number of ways to form a committee and then pick its chair would be n choose k times k choose one. And that's what this side says. An alternative way of doing this, again, as a two-step algorithm, is to first choose somebody to lead the committee. So choose the chairperson from the general membership. Do that first. And then secondly, pick the rest of the committee that goes with that person. So choose the other members of the committee. If I do it that way, then the number of options for choosing a chairperson from the general membership is just n choose one. I'm going to pick one person from all n people that are in this organization and say, you are going to be my committee chairperson. But I need to also pick the committee for them to chair. But the chairperson's on the committee, so we only need k minus one more people from the remaining n minus one people. So I'm going to choose the other k minus one people from the remaining n minus one people. So therefore, with this approach, I would have n choose one times n minus one choose k minus one ways to do this. So these are two completely legitimate ways to do the same problem. And so that proves that the two answers have to be equal to each other. If it seems surprising to you that these answers are the same, just pick a value of n, a value of k, and evaluate them for some numbers, and you'll see that they really are the same thing. And if you think about how you're evaluating them, you'll see it's not all that surprising that they're the same.